Alright, so let's take a look at some of the basics. Chemical formula. That's what these are right here. Chemical formulas. The subscript tells us there's 2 sodium. We don't write ones for that, so that means that there's 1 chromium and 4 oxygen. Parentheses just work a lot like the same like they do in math. When we have the subscript 2 outside of the parentheses, that means there is 2 NH4s. So let's say 1 and 2. We don't distribute the 2. That means something different if we were to say N2H8. But there are 2 nitrogens and 8 hydrogens in total. We got 1 sulfur and 4 oxygen. So that'll play a role when we're naming and doing things later in the year also. As far as naming positive ions, they're super easy. It's the element name and then the word cation. I often will just say lithium ion because I know it's a positive ion, and sodium ion because I know, again, it's a positive ion. It doesn't have any possibilities it could be. So whether you said cation or ion, it's not really going to make any difference. Negative ions are a little bit different. So when we're talking about negative ions, the idea is that the ending of the element is dropped, and then add IDE. Usually it is the last syllable, but it doesn't have to be. There's probably one exception I can't think of right now. But the idea is the oxygen becomes oxide. Chlorine becomes chloride. So for the most part, when we think about IDE at the end, most of the time it's an element. There are some polyatomics, but since you have that polyatomic ion list to use, there should be no mistaking elements from ions that are polyatomic. Alright, so let's take a look at some examples here. So if we're trying to determine the ionic compound from the ions, first we need to know the charges. So the idea is I'll put out a couple examples, like let's say strontium and oxygen. So you should see and know the pattern that because strontium is in the group 2, it will have a 2 plus, and because oxygen is in the group 16, it'll have 2 minus. So when we mean by crossing the charges, we mean crossing them down to the subscripts. So kind of crossing this way, crossing that way, giving some direction. So we would have this idea of SR2O2. Now because we know ionic compounds are about the ratios of ions, it's always the lowest ratio. That's why this would be reduced to the SRO for strontium oxide. We don't accept things like SR97, oxygen 97. That doesn't work that way for ionic compounds. Covalent compounds are a different story, but we'll get to that later. Another example would be something like chromium and phosphate. Now phosphate has a 3 minus charge. Chromium in this case has a 2 plus charge. It is a transition metal that can have a varied amount of charges. In this case it's 2 plus. We'll get to how you determine that a little bit later. So again, we cross this down to the subscript. Boom, boom, boom. There we go. And so we'd have 3 chromiums. And then because phosphate is a polyatomic ion, it needs to be put in parentheses in order to be having the proper ratios of the ions. Last example, barium and chlorine. Again, barium 2 plus, based off where it's at, chlorine 1 minus, subscripts, in which you get BaCl2. The whole reason of the crossing the charges and reducing, if necessary, is to get equal and opposite total charge. You can go that way if you'd like, or you can follow the simple technique and be able to get the correct formula each and every time. Alright, so let's take a look at a precipitation reaction where this crossing of the charges is more commonly used. Opposite charged ions attract each other. Now, as a compound, they were already attracted to an oppositely charged ion, but if we have a chemical reaction occur, this new pairing will form, creating new products. And they follow this formula pretty straightforward. So let's take an example look at this first one. So, in the idea here that the charges are as follows, you would know these by either knowing them or looking them up on your reference sheet. So the sodium is now going to be paired up with the other ion, that's the opposite charge, and that would be the nitrate. Likewise, the silver ion will pair with the chloride ion. In doing so, they have to pair together in the correct ratio in which crossing the charges would occur. Since all of these are 1, all of the subscripts would not be drawn as 1. Remember, nitrate is one object. Don't look at this 3 and thinking that it's a separate entity. If we continue down to the next example, ammonium is a 1 plus, nitrate is a 1 minus, copper in this case is a 2 plus, and sulfate is a 2 minus. Now when we repair these up, we have ammonium with the sulfate and copper with the nitrate. Now keep in mind that we have not combined these to have proper formulas yet. We would need to cross the charges. So again, we got our 1 plus, our 2 minus. So if we cross down the charges, that means I will need 2 of these for every 1 of the sulfates. 2 plus for the copper, 1 minus for the nitrate. So 1 copper and 2 for the nitrates. This would give us correct formulas. Now for our last example, again we want to know the charges, 2 plus, 1 minus, in this case 3 plus and 3 minus. So again, when we bring these new couples together, calcium is with nitrogen and iron is with chloride. Again, we want to look at the charges, 2 plus, 3 minus, in this case 3 plus, 1 minus. So when we cross the charges, we'll have 2 nitrogen, 3 calcium, 3 here, and only 1 of the iron. This would give us our now correct formulas that we'd want to take and determine which one is soluble or dissolves in water. That we'll be doing in a future lab. Alright, let's take a look at going from a chemical formula to a name now. So if we have no transition metals that have different charges, it's very simply put the cation then the anion. So for example, these are both elements, none of them transition metals, so we have lithium, and then iodine becomes iodide. Zinc is a transition metal, but it only has a charge of 2 plus, so it follows the same rules as before. This is zinc, no Roman numerals, sulfur becomes sulfide. K2O, K is potassium, oxygen becomes oxide. On the other hand, when we have things that are transition metals, we need to indicate what their charge is, and we use that in Roman numerals. So we have iron, and its current charge is 2. So we put iron 2, sulfur becomes sulfide. Now over here, iron, again, but this time it has a 3 plus charge. However, it's still iron 3 sulfide. We'll get to how you understand it to be a plus 3 or a plus 2 in a moment. And again, copper is copper. Its charge is 2, so you need to indicate it is a 2 oxide. And based upon this simplistic Roman numerals, we can determine what the actual chemical formulas are just from either the name or the symbol itself. Alright, let's take a look at determining those charges. So I'm going to use the same examples as before, just to keep things kind of focused. So again, you first want to look at the anions, the negative ions. Those are always consistent. They don't change when we talk about ionic compounds. So sulfur has a 2 minus charge. So because there's only one of these sulfurs, the total negative charge is 2 minus. In an ionic compound, the total negative charge equals the total positive charge. So the total positive charge is positive 2. Because there's only one iron here, that means this one iron has to have a 2 plus charge. Roman numerals indicate what's the charge, not how many there are, but what's the charge. So that's why we get the idea of iron 2 sulfide. Now it makes going from the name to the compound easier, is this is the charge, so if that's the charge, you know this is 2 plus, you would know sulfur is 2 minus, cross the charges and reduce. Going from the name to the compound, the chemical formula is way easier. Looking at this example here, sulfur has again a negative 2 charge, or 2 minus charge. Because there's 3 of them, it has a 6 minus charge. That means there needs to be a 6 plus charge. Because there's 2 of them, that means each iron would need to have a 3 plus charge, which is why we have it as iron 3 sulfide. Likewise over here, some students will go, oh, I'll just uncross the charges and it'll be awesome and everything will be right. No, that would have you think of a different rule that doesn't always work. My rule works 100% of the time. Again, if you tried to uncross the charges, you'd tell me that copper has a charge of 1 when it doesn't. Oxygen has a 2 minus charge. Because there's 1, it's 2 minus. Copper then would have to be 2 plus to counteract the 2 minus. And because there's only one copper ion here, it has to have all of the charge. That's why it's copper 2 oxide. Likewise again, if you were to go back from this and you have copper 2 plus, oxygen 2 minus, you cross it, you reduce it, and you get your CuO as your chemical formula for copper 2 oxide. Alright, so one last little thing here, just giving you some, again, further practice here. Tungsten 4, oxygen 2 minus, 2 and 4, and reduce. That's why I get WO2. Platinum with its positive 1 charge, sulfate with its 2 minus charge, cross the 2 from the sulfate down here, 1 for the platinum, PtSO4. Tin with its 4 plus charge, chloride with its 1 minus charge. You can clearly see that would become your SnCl4. So again, going from the name to the formula, way simpler than going to the reverse. It takes more steps to go backwards. But again, you need to be familiar with being able to do both.